No, I'll just. Thanks for coming, everyone. Today we have Lionel Mason. He's professor of mathematics at the University of Oxford. Lionel did his grad school at Oxford, his junior research fellowship at Oxford, and then he decided to stay at Oxford. So he's basically
That's how it works.
yeah, that's how it used to work. And well, his main interest has been twisted theory, and over the course of many years, he's applied it to various things like differential geometry, to integrable systems, and over the last 20 years to the study of scattering amplitudes. And today is going to tell us about, and he was my PhD supervisor as well. So a little bit of cronyism doesn't go too far if he's already in the vicinity of Boston. Anyway, so he's going to tell us about some cool work on gravitone scattering in black hole backgrounds. So field black hole backgrounds.
Well, thank you very much for inviting me. So I kind of sort of, no, I shouldn't. I was about to confess that I sort of, not only did I spend all my time in Oxford, I met my wife there, and one of the reasons I encouraged Atul to invite me was because she's getting some award this weekend. So. So I have to thank Atul for
Next time we'll invite her.
Well, you have to be interested in population dynamics for that, population genetics for that. So today I'm talking about scattering yourself to your black holes, but this is part of a bigger program that I've been studying with lots of friends over the years, based on twistor theory, but I was warned that for the purposes of a colloquium, I should strip out all the twistors. So here I am talking about something that this is really meant to be so we've been studying sort of using twistor methods for studying gravitational scattering for some years, but this is the first time we've managed to sort of get something that looks a little bit like a black hole. But you will see this qualification here of the word self-dual, which may take those of us with long memories back to the 80s, perhaps. But anyway, let's okay. So first of all, then, one of the things that I have been trying to do, or we have been trying to do, is to study amplitudes on non-trivial backgrounds. And so there's a huge community now of people working on perturbation theory around flat space. But if you work on a nonlinear background, you can sort of encode some fully nonlinear effects. And in some sense, you could be summing infinitely many loops in the scattering amplitude approach to classical gravity. And some of the parameters you might be able to get data on that are exact to all orders. But you've got plenty of challenges if you want to do that. So one of the things that you're going to have to do is to think about the scattered particles. You've got to construct momentum eigenstates or analogs of momentum eigenstates. And then you've got to set up your flat space perturbation theory on this curved background. So constructing a propagator, for example, is going to be a challenge too. And then you've got to do the integrations to do the sort of the perturbation theory. So this is all sort of really heavy duty stuff when you start thinking about the details.
When you say, so sum up loops, sum up diagrams to all orders, but do these methods also help you with like genuine non-perturbative effects like instantons or,
Well, that's the idea yeah. I mean, some of the parameters, it's unclear which parameters are there to all orders and which are not. But I mean, but you might expect if you could do these sorts of things on a curved background, then you would have a full non-linear dependence on the spin rather than perturbative.
Right. I guess there's a difference between being able to sum the Taylor series and being able to include like these e to the -1/g effects, right? It wouldn't necessarily be an exact result unless you could.
Well, you see, you're going to be perturbative in some parameter.
Yeah.
But certainly, but not all. That's so you get more information. So that's the hope. And when you look to see what's been done, there's not a lot really. I mean, so you can do quite a lot on generic plane waves. So so we started there back in 2018, but you get up to 3 and 4 points before you've got to start sort of worrying about propagators and integrations and such like. And there's an awful lot done on ADS and Datissa, so on homogeneous spaces, but there it's already quite tough. You know, so maybe these endpoint, I forgot what the U is, maximal something violating the U1 symmetry in supergravity. But these are all still homogeneous spaces, but you know, without your regular Fourier analysis, it becomes harder. But one of the things that Atul and I and Tim did in Atul's thesis was to sort of start working on self-dual radiative backgrounds. And so the idea was that this was a class where you could use integrability of the self-duality equations as a tool and to try and get you past some of the technicalities. And but there's a problem which I'll explain a bit more in a moment, which is that those things did not extend to anything that looked a bit like a black hole. So the so-called radiative condition rules out black holes. So I'll say a bit more about what that means, just to give you some picture, and just to give you a little bit of a history as to where some of the integrability ideas are coming from. So so first of all, if you're interested in just an asymptotically simple space-time, so there's no black hole, then you can hope that it goes out smoothly to infinity, and you have this kind of Penrose picture of infinities being sort of the light cone of a point at I plus, union one at I minus, both points at time like infinity, and then these are null infinities where all the radiation goes to. And Ted Newman had the idea to try to rebuild space-time from data out of infinity. And so the idea is, how do you reconstruct a point? Well, you see where its light cone intersects infinity, and he wanted to see if one could characterize these kind of light cone cuts, as he called them, from just data at scry. It's a bit of a tall order, and he wrote down
It's what we now call holography, right?
Yeah, absolutely, absolutely. And it's a bit of a tall order, but what he did do is he wrote down a beautiful equation, a so-called good cut equation, which was going to constrain this cut. So it's an equation on this z function, but he wrote down a complex equation in terms of the the self-dual part of the data at null infinity. So self-dual in the sense of being circularly polarized, left-handed. And so he got a well-defined mathematical framework, and he reconstructed a space-time, but it wasn't the one you first thought of.
You mean the space-time metric, or like by reconstruct space-time, do you mean like find the metric in the interior? Or
yeah, so he found a complex metric on the interior.
Okay.
Whose data agreed with the shear at null infinity.
In holography, we don't typically reconstruct the metric itself, right? We construct like integrals of the metric.
This was 50 years ago.
It was a little.
And
Yeah,
I think the fact that he was trying to take data, the theory on the boundary, and regard that as fundamental and reconstruct the interior.
Is very prescient. Yeah.
Yeah.
Yeah, and it was a beautiful
holography.
it was a beautiful thing, even if it wasn't sort of, you know, giving you back the original space-time you thought of, even if it wasn't holography in the sense that we currently understand it, of giving rise to fascinating strong weak dualities and so on. So anyway, so he ended up with this complex self-dual space-time as a result, and this then, yeah. So Roger Penrose then tried to understand this, And so Roger Penrose sort of introduced a twistor space attached to Scribe, which encoded the asymptotic data, and he reformulated this whole thing in twistor space, which generalized this whole thing, and somehow it expressed how it is you could think of this light cone cut construction as something. It's not necessarily tied to null infinity anymore, but you could think of it as an integral system. You have this auxiliary problem out of solving for these cuts here as this z function as a function of pointed space-time and the coordinates around Scribe. But now Penrose was doing it in twistor. He somehow lifted it to a twistor space. So this here takes you up to 1976. Then the work that we've been doing starts off from this work from back then, way back then, to sort of try to extend it to give you amplitudes now on these self-dual backgrounds, which was allowed to start sort of expanding around these self-dual backgrounds and to reconstruct data about the real physical Lorentzian space-time that you're actually really interested in. So that's what the work we've been doing is focused on. Okay, so what sort of things do you get out of this? Well, just to give you an idea of the sort of things, I'm not going to go through the whole story here, but I just want to talk about a part of what Attal has in his thesis. So I don't know how comfortable people are here with two component spinners. So you can so this is just a way of rewriting standard 4 vectors as 2 by 2 matrices in such a way that the determinant of the 2 by 2 matrix is the length of the 4 vector. So if you just take this, this is the standard expression for doing that. And one of the things that happens here then is that if the vector is null, so all of your on-shell momenta have got to be null vectors, then the determinant is 0. So this 2 by 2 matrix factorizes into a row vector times a column vector. And this has been invaluable for the study of scattering amplitudes over the last 30, 40, I don't know, yeah, 30 years at least, 40 years maybe, because you can then write down invariants here, which just depend on these constituent spinners. And what's nice about that is that these actually contain these, because the extra phase you get from this, so this, you can absorb a phase one way or the other, but that phase encodes the polarization data. So that's it's not a bug, it's a feature. You get an extra phase in these spinners. And then you can express amplitudes in terms of these contractions of two component spinners. And these are chiral, so the undotted ones are anti-self-dual, and the dotted ones are self-dual, and they will tell you about the handedness of the various particles involved. So to give you an example of why amplitudes look so good in spinners, that sort of, I'm giving you a little bit of a cartoon of this formula because I didn't want to clutter it too much. But the in 2012, Andrew Hodges wrote down a formula for the gravity scattering amplitude of tree level with two negative Felicity gravitons and the rest positive. And what plays a role in this is this very simple sort of square bracket over angle bracket structure for the spinor momenta. So there's a matrix here which you construct out of that with its off diagonal entries, and then you make the diagonals in such a way that the row sums are vanishing. And the and once you've done that, then you find that the answer is a very simple just reduced determinant of this matrix, because it's row sums are vanishing. It's obviously got a 0 eigenvector, but you can define a reduced determinant. Something right that Marcus Stengel points out. I left out some factors. But, anybody who knows it properly. But Anyway, so this is why is there such simple structure here? Anybody who's done perturbation theory for gravity will know that it explodes. I mean, the heroic price to width calculations for 4 particles, and many cover pages. So why is that? And there were some cute things that happened. So then Bo Feng and Song He sort of so in fact there's an older story from Steve Byrne and friends who so Song He and Bo Feng noticed that you could think about this as a matrix tree theorem for a sum over tree diagrams with propagators given by this structure here. And so this is something that Steve Byrne and friends had noticed sort of some 20-something years ago, course of a century, I guess. And this sort of begs the question as to what theory is that? And so anyway, I sort of answer that in this thesis, and you find it's for this sigma model in twistor space. That's the theory which actually defines this formula, and that sigma model in twistor space is Penrose's reformulation of Ted Newman's light cone cuts. So that was the yeah. So that's a beautiful thing. So okay, so we've managed to sort of give an understanding of where.
Sorry, I missed that last sentence. In the usual discussion of this, you don't need to refer to the Newman Penrose. You just write down the MHV, and then what was the simple connection you said there? The sigma model is what for Penrose's?
Yeah, sorry. So okay, so this stuff is all done with soft limits and stuff, and it's standard amplitudology, where there's a long history there of that amplitude type law. But so the sigma model we wrote down is a sigma model that has this term here as the propagator, which is what you'd expect for the matrix tree theorem for tree diagrams with these propagators, and essentially, so the sigma model was really for maps of the Riemann sphere into twistor space, but that was really just Penrose's reformulation of Ted Newman's light cone cuts. So Ted Newman had a good cut equation, and you could just as easily write down an action for that equation on Scry, and well, you can, and this is just a lift of that, and that's what this sigma model is. So yeah, so to a certain extent, this correlation function that's giving this is just goes back to the Newman story.
That's the correlator, not the integrated correlator, right? We're not doing string theory here.
No, it's just
This is a tree level classical correlator.
Yeah.
This is very this appears to look like celestial CFD, so to speak, just a correlator. Second approximation of celestial CFD.
So you really wouldn't do that in string theory, or whenever you write.
When you said integrate, there's no loops here. Right?
No, I mean,
Integrate over moduli.
yeah, do you integrate over moduli space? On
Well,
that
no,
function?
but you have, because that's where the momentum concerning delta function here came from.
Yeah, I think
So
this is a full correlate.
Yeah, okay.
But for example, in David Skinner's twistor string, you'd be a full quantum correlator, whereas in this model here, it's a tree level correlator.
There are no Walsh-Sheen tables.
I was just asking if there were Welsh intervals, which there are not, yes.
Well, no, but they're all localized by delta functions.
So they're operators on the celestial sphere.
Well,
Okay.
yeah.
It's supposed to be this semi-classical approximation, like if you only take one contraction, take a semi-classical limit, then this correlator computes this MHV amplitude. It's like supposed to be an approximation to celestial CFD in the MHV sector. At least that's how I.
That's
Okay.
the words appearing in your thesis.
Yeah, but that
So okay, so that's the sorry, this is a bit of a hand wave just to give you an image as to what the twistor theory was doing. And then what can you do with it? Well, you could then say, suppose somebody gives you some asymptotic data at null infinity, and you can use the Newman construction to derive a self-dual background. And then you can sort of ask the question, can I now perturb around that background to try to reconstruct the true, something that's approximating the true Lorentzian solution? And so the first thing you might want to do would be to generalize that formula that Andrew Hodges found at tree level. And what you discover is that because of the integrability of the self-dual background, various good things happen. All those kappas, those kappa I alpha that you had, which just ordinary constant spinors on flat space, well, you have constant anti-self-dual spinors on a self-dual background. So these all actually survive nicely as constants. But the background is curved, and so the dotted spinors are curved on the self-dual background. But then you discover that you can actually write down momentum eigenstates on the self-dual background, and you have a dressed version of these spinors and a dressed sort of what I call here double bracket. And so with that, you can define a dressed version of this Hodge matrix that we had on the previous slide. And but now you expect there to be sort of more junk going on. You know, this isn't a flat background. You expect the gravitons to sort of bounce off the background. But you can argue that with n particles, you can have no more than n-2 interactions with the background. And so roughly speaking, what you're doing is you're making the quadratic term part of the propagator on the world sheet. So the so you've got 3-point vertices. So you can only have at most n-2 interactions with the background. And
these n plus particles.
Yes. So sorry, we have 2 minus and then n-2 plus. So we've got two. You have to have to get a non-trivial amplitude. You have to have at least 2 minuses in the game.
Is that still true in a background?
Yes, on a self-dual background. So self-dual background you think of as like a cloud of plus particles, and then so if you put more plus particles on there, there's not going to be any scattering because it's an integral system. And in fact, even if you put 1 minus particle on, there's not going to be any scattering. So you need to.
It's true in self-dual Ricci.
Sorry, you've probably got some exceptions. Okay.
That's still tree level statement.
Sorry, self-dual is Ricci.
Conformity
self-dual means wild self-dual.
But he
Yeah.
to it real okay.
And this statement was about tree amplitude so far, right? In curved background or?
Yeah, I haven't. We don't know what.
I think these are all just trees. Yeah. I mean, what's interesting, I mean, it's a separate discussion perhaps. What's interesting is the extent to which you can get the all plus one loop from the sigma model as well.
Yeah.
But so the
You're going to say something about that?
no, not today.
No, that's
Okay. Anyway, so really, what I wanted to say here was simply that you get a matrix for this MHV amplitude on the background. You get a matrix which is slightly less than twice the size, or well, 4 times, I guess. Twice the size of the one we had before, and you can generate. I don't want to write out the full solution, but you can generate the full background coupled MHV amplitude from reduced determinants of this matrix and its derivatives. And the formalism just works really surprisingly cleanly.
And reduced determinant here means it's still 2 rows and 2 columns of this guy, or because
Yes.
before it was 2 rows, 2 columns, but now you've enlarged the matrix, but you still only relate 2.
Yeah.
Okay.
So we can't have a particle, a positive velocity graviton can't orbit around the self-dual. There are no photon rings around self-dual black holes. Because
there are no self-dual photon rings around the self-dual black hole, but you might get an anti-self-dual one. I don't know, that's a nice question. Yeah, I mean, actually, I was having.
Because you have an only finite number of interactions, so you don't get you never get a
No,
finite
you never,
deflection.
no, that's true. That's also true. But it's a nice question whether there's an anti-self-dual ring, proton ring or something. Anyway, so why was I too embarrassed to give you more details about this in a black hole in BHI colloquium? It's because the term radiative that we use here means that it's a solution that's defined from its radiation data at scry. And that specifically excludes black holes because the radiation data is 0 for black holes. They tend to be stationary, so there's no shear, there's no radiation data. And so it doesn't apply there. So with all this sort of excitement in the community about black holes, especially in a place like this, we felt like we were a little bit spare and on the side, and so we thought that we had to try to upgrade our work to deal with black holes. So that's what this work is about. So I've got an outline there, but maybe I mean I've got till 12, have I? I mean I can. Is that normal? I'll just look at the list here. And see.
5 minutes less than 12.
5 minutes less than 12. Okay. Well, we'll see how far I get through this. So first of all, I just want to talk about self-dual black holes. I want to talk about you see what so what this talk about is what we could say about working on self-dual black holes without actually having to introduce the whole palaver of twistor theory. And so basically what happened was that Assel started sort of computing away. And then at some point we saw you can strip out, you can just do this by hand, and so and so this is what happens when you strip out the twistor theory from a calculation. These are the structures you get, and so you begin to see the what's driving it is that you've got some charged killing spinners for the self-dual dions, and that allows you to construct momentum eigenstates on the self-dual dions, and then you get this just direct lift to self-dual tau now. So there's really very little work to do to actually that first step that I thought, saying was already a hard thing to do on a background, which is to find the analogs of momentum eigenstates. And there's some curiosities though. There's some non-trivial topology, so I'll talk about that. But also the formula is simple enough that you can actually do the integrals to at least do the 2-point functions. And so this will tell us about two anti-self-dual particles on the background, which is really a story about a self-dual background. The negative helicity particle comes in, and then its helicity gets flipped by the background, and it bounces off in some other direction. So, and I'll say a bit about spin. So, here you go. Okay. So, so since I'm going to be talking about killing spinners, there's a beautiful story going back to the 70s about the relationship between between black holes and their killing spinners. So this is a feature that all the things that you think of as black holes have in 4 dimensions, if they're vacuum or even the cosmological constants. So they all have Petrov type D, and that means that you can write the Weyl tensor. So you can always factorize a 4-index tensor into constituent spinners. But what's interesting here is that they double up. You get 2 microns and 2 ions.
Sorry, but the Petrov type D is for black holes where there's only one black hole in the solution. Otherwise, they would not.
Yes. Oh, sorry. So you're thinking about the Majumdar Petru or something, or
right.
the Marty. Okay. Yeah. Yeah. I was. Yeah. So maybe I should use the word single. Yeah. 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 That's true. Yeah. So anyway, out of a micron, an iota, and some power of psi2, you can construct this killing spinner. That's what they show. And in fact, the formal relationship is I mean, you can go forwards and backwards essentially. So I've just given you the backwards here. The psi is given as chi over chi to the 5th, where chi is just the coefficient here, and then you can work out what the relationships are between chi and the psi2 and the micron and iota. So these
is that I didn't realize this. You would call it a spinner even though it's two indices?
Well, it's valence too, but I guess it's, I mean, you could say it's an anti-subdual
Yeah.
form.
Yeah.
I mean,
That's the Killing-Yano tensor. Right?
yeah, it's
Or
the
the
subdual
Killing-
part
yeah,
of the Killing-Yano tensor, that's right, yeah. But I guess Penrose and Walker back in the day sort of,
Called it a spinner.
yeah, I was brought up that way, sorry. I learned about Killing-Yano tensors later. Okay, and so in this story then, you have a killing spinner, and of course, this is a Lorentz real story, so that the dotted things are all complex conjugates of the undotted things. And so the self-dual parts are all the complex conjugate. And in many ways, this is one of the easiest ways to understand the geometry of the Kerr in the sense that in the original, so Kerr's original paper has a natural flat background, the famous Kerr-Shield flat background. And in those rectangular coordinates, this killing spinner is just this. It's just in fact, this is its flat space version, and so it's just linear in the coordinates with this little sort of imaginary shift in the z direction, and where a is the Kerr parameter giving the angular momentum, or angular momentum per unit mass. And in fact, this observation is well, I guess the Newman-Janis shift was before that, but it gives you a way of understanding the Newman-Janis shift. So they constructed Kerr from Schwarzschild by sending z goes to z minus IA in some terms of the metric, and z goes to z plus IA in other terms of the metric. And you had to sort of somehow have a bit of black magic to know which was which. But here it's clear. It's the anti-self-dual part goes to z minus IA, and the self-dual part goes to z plus IA. So when we come to the self,
It's black magic why that works, right?
it's black magic at the level of the metric. You know, so you didn't know that you could just start off with a killing spinner and then write down the metric, I guess. But it's not black magic in the self-dual sector because sorry, well, I say that next. So then what's the self-dual version of all this? So first of all, you have to get a self-dual metric, you have to think about the Schwarzschild together with its nut parameter. So self-dual will always mean that the electric charge is you know, I times the magnetic charge in Lorentzian signature. But in Euclidean signature, you can have the electric charge equals plus or minus the magnetic charge. So first of all, we actually work in Euclidean signature, and then you're doing the self-dual output. And it has this very simple form. It just depends on a potential V, which is for self-dual tab has this very simple form. And then this A here it is a connection whose curvature is given by the gradient of B. So it's a monopole equation. And the A that you need there, the curvature would be the volume form on the sphere. This A has is something which you need a gauge choice to write down. So this is a standard gauge choice that people use. And I'll talk a bit more about that topology of that later.
This A has nothing to do with the rotation.
Oh, sorry, no, this is a bold A.
Yeah.
Yes, sorry. And anyway, so this is a self-dual metric and it's type D. And so again, the previous ideas apply, but of course, we've only got the self-dual part of the curvature. So and then for this, there's a self-dual valence to killing spinner, and that's this same killing spinner that we expected for really Schwarzschild. It's the A equals 0 case. But now there's no mystery in the Newman-Janis shift. You're not putting Z goes to Z plus IA or minus IA in different parts of the metric. Here, just the whole thing, you're bodily shifting it or analytically continuing it in the complex.
The other spinner was 0 anyway, right? So we couldn't shift.
Well, yeah, it wouldn't have done anything. So that's right. So what I'm really trying to say is that actually doing self-dual tab does the self-dual part of Kerr as well. Okay. Now, anybody who's been to an amplitudes talk will have heard of the double copy, I guess. I don't know. So anyway, but doing things for spin 2, you start off by doing things in spin 1. You know, it's always easier. There's fewer components, and you learn something. So what's the spin 1 version of this? This is the self-dual Euclidean Maxwell dion central, but you've got E equals G plus 1 for the self-dual case. And so this is the potential then, which is this is the same bold A from the previous slide, but it's got a Coulomb. So this is the magnetic monopole, and this is the electric monopole, this gives rise to a self-dual field. So this is what we think of as the single copy of self-dual tab nut in the double copy story. And I was going to say something about the topology here. So if you put a factor of a half here, then well, so this formula here has a wire singularity of p2 equals pi, because when p2 equals pi, you've got a naked d phi even at the axis. Anyway, that has a pole, and you have a wire singularity, but you can get rid of the gauge transformation, and the gauge transformation is going to be e to the minus I phi, but it's going to you need some periodicity. Phi goes to phi plus 2 pi to make this a consistent thing, which of course you have on the sphere, and then you can move this singularity to 0. But what you want to know about this, of course, is that this is the full connection is a connection on a topologically non-trivial line bundle with Chern class 1. And so that's why I've chosen this harvest to have Chern class 1. And you can have a whole sequence of line bundles with quantized charge a la Dirac. So it's, of course, it's all well known to Dirac with this connection. So this is the single copy. And following the sort of double copy kind of mode, then you work out what you want to work out for the single copy, and then you double it.
Sorry, the wire singularity is also at the level of the geometry?
Well, by the time you go to the self-dual tab nut,
Right.
yes. So there's there's a wire singularity in the metric I wrote down on the previous slide. But of course, so that to make this regular, that entails a periodic identification of T, and again you have that gauge freedom. So I mean, really, you see, you're trying to make this look like something that's a 3+1 back hole with the spherical cross section. But when you actually know what this really is properly in R4, here you've set things up so that R equals 0 is the horizon in your Lorentzian signature, but in Euclidean signature it's the axis of symmetry, and it's a regular point, and it's actually an axis of a symmetry. It's like an origin inside R4. It's a single point.
It can be thought of as a horizon and split signature.
Yeah, that's yes. So, okay, so the charged Killing spinners are going to be key to our story. So in this self-dual case, we had the dotted chi, but this undotted chi has a nice relationship to the self-dual dion. So what's going on here? Well, we can factorize this in a similar spirit. And if we so this is something you can always do, and I'm just normalizing it so that sort of chi plus and chi minus have the same sort of length. And there's a phase ambiguity there, so you can fix the phase ambiguity by choosing some stereographic coordinate and just writing out what this factorization does here. But these are actually singular as theta goes to infinity, and but then you can sort of think of them as, when you think of them as sections of this line bundle, they're no longer singular. They are just simply global sections of this line bundle. And once you know their global sections of the line bundle, you can then ask whether they satisfy an interesting equation, and the answer is yes. So these are charged killing spinors for this self-dual dion. And so they satisfy this equation. So very good. So you have these special charged spinors coming out of, as I say, the anti-self-dual thing that you thought of as a killing spinor. And
So here A is the background potential for the dion still. Right?
this is
So
the
we're-
diol. Yeah,
the dion
it's the minimal diol.
written in spinor limitations.
Yeah. And so what's this good for? Well, you can start off with a flat space massless field. So this is just satisfying the massless field equations on flat space. And then it's an elementary calculation that's done in other forms in Svenderson spacetime, whereby you can, if you start off with such a flat space spinor, then you can contract chi plus or minus into it, and this would be a solution to the massless field equation, but now with charge E, because chi plus or minus has got charge plus or minus E. So this allows you to construct background coupled fields from fields that are not background coupled. So that's the first step that we're going to do. And so this is how we can construct analogs of momentum eigenstates. So you start off with your standard flat space momentum eigenstate. So you have ECI k dot x, your familiar plane wave, but this kappa here has to be one of the spinor factors of the momentum. And then you can sort of get a charge P minus Q field by multiplying by this, but by basically contracting with P chi pluses and Q chi minuses. And you get a field which is roughly speaking going to look like this. So it looks like a plane wave, but you've got some, really this is some spherical harmonics thrown in. And you get a bit of inflated growth in R that are really associated, come along for the ride with those spherical harmonics. And so the minimal version of that of the given charge then is just to use the pluses for positive charge and the minus is for negative charge. Otherwise, it's like you're putting in an extra spherical harmonic there, boosting up the angular momentum.
Could you have gone into a conformal basis?
So by a conformal basis, you mean
You've still got, well, I forgot what signature you're in here, but you've still got an SU2 or an SL2R or
so you're talking about using a conformal transformation to
no, instead of diagonalizing asymptotic translation. I mean, translations are
oh, I see what you're saying.
translations are broken.
Yeah.
So, but there's some subgroup of
I see. Well, I mean, certainly taking it out to infinity, we could have considered some celestial type wave functions here as well. I mean, so whichever basis you liked in flat space,
let's see.
you could have jacked these things up to.
But these things have a symmetry, right? They have an isometry.
These things all have SO3 cross R symmetry.
Oh, I see. So,
Well, it's really actually it's really an SU2 symmetry, isn't it? Because because it's all twisted. But yeah.
yeah, okay.
Okay. Anyway, so this is the first part of our problem solved then for the self-dual dion fine momentum eigenstates. And so these so you might say, well, perhaps I also need some positive velocity things as well. And you can do that too. Once you've got your solutions to the wave equation, charge solutions to the wave equation, then you can sort of jack up their helicity by thinking of them as sort of potentials of various forms for so this is the example you'd have for Maxwell. So I mean, this also works, of course, if you've not left with any indices here, so you get solutions to the wave equation. So yeah.
So I should think of the phi as some tower of spherical harmonics of some massless charged particle, or maybe I misunderstood, or like the most general phi you wrote down, what? That's
So,
all
this
equation, I mean-
general, yeah, these powers of zeta could be wrapped up into spherical harmonics. That's right.
Okay, but these are like massless charged particles that solve this
Yeah,
first order equation.
that's right. That's right. Yeah, so and there is this point that the charge E then gives you a minimal number of spherical harmonics. You know, there's a minimal spin that you've got to have because it's got this minimal. The charge E is correlated with the spin bond, and this comes along with its own sort of growth in R. So that is a bug or a feature depending on which way you looked at it. We decided just to leave that ambiguous.
Schwinger also had this.
Yeah. It's a known phenomenon, I suppose. It's yeah. So the next task is, well, so in the spirit of the double copy, then you've done the self-dual dion. What's this got to do with fields coupled to self-dual tau nut? And as I was saying before, that you had to have a periodic time which quantizes the frequency. So if you've got an e to the I omega t in there, then that periodicity means that your frequency has to be 2m omega has to be an integer. And
What signature are we now?
well, we've been doing all this. I was going to have one or two comments about split signature at the end, but this is we just sort of brutally followed the kind of Gibbons-Hawking code logic and stuck to Euclidean signature.
Well, but there's no scattering in Euclidean space, right?
No, but this is analytic continuation. So that is to say, you have Lorentzian wave functions, which you then, I mean, you've got to decide.
So the scattering states are exponentially growing at infinity.
Right, but then you think about doing it in the contour and so on and so on, doing intervals on a contour. So really, that would just because you've got the symmetry in time. That's really just a question as to how you think about the time interval, and because it's. Because time's a circle, in fact, it becomes a Fourier series. So it ends up being relatively straightforward.
So we're taking external momentum to be complex, essentially.
Yes.
Okay.
Yeah. Anyway, so to get these things coupled to a self-dual tab nut, we just have a rather nice result, which I think is implicitly already in an old paper of Don Page's, I think, where he computes the propagating on self-dual tab nut. So the statement then is that if you have a solution to the background coupled self-dual dion equation, then it naturally lifts to a momentum eigenstates on the self-dual tab nut. So as you replace the electric charge by 2m omega by this frequency. And the way this works is really just naively, you just write out the frame like this for self-dual tab nut. So this is an orthogonal frame for this metric. And what you see is that this. But when you write it out, this is really just up to this overall scaling. It's really just the ordinary derivative as the ordinary flat space frame plus 4m times the self-dual dion times d by dt. So if you've got energy omega, then this gets to be replaced by omega. The d by dt gets to be replaced by omega, and you can see that the massless field equation reduces to the one that we just solved. So that's very simple. And so basically then the charge gets replaced by n. Okay.
So this is not, when people talk about double copy, and they usually mean squaring an amplitude, but here we're literally saying the metric is the square of this.
Yeah, I mean it's somehow the the potential is somehow being related directly to the metric.
Yeah.
Okay, so we've got we've got all of our momentum eigenstates on these backgrounds, and so we can now try to do some 2-point functions at least, and so the intuition is that self-dual backgrounds correspond to many plus particles, and on flat space the all plus amplitude vanishes and the all plus and 1 minus amplitudes all vanish. So for 2-point functions we expect the plus plus 2-point functions vanish and the plus minus 2-point functions vanish. So that's our expectation, but we expect to get something non-trivial with 2 minuses. And in fact, supersymmetry in flat space would also give you a lot of other things vanishing where you sort of have different fields in the multiplet.
Sorry, well, the plus minus 2-point, does that vanish in flat space?
Yes.
It's not the propagate, it's not the English propagate.
Well, this is plus minus in terms of taking the variation of the action and evaluate it on the plus fields and the minus fields. So I guess there's no scattering, so that's probably just the difference between the inner products at scry plus and the inner products at scry minus.
I see.
So it's more non-trivial on the self-dual background. But it's a reflection of the fact that the self-dual sector is. So the way that I'd say it is that the vanishing of this one is the condition that the self-dual sector is consistent as a set of differential equations. Vanishing of this one is actually a statement that there's no scattering within the self-dual sector, which is a statement that the self-dual sector is in some sense integral. Because the minus particle measures how a plus particle might change as it goes through the space-time. And the point is it doesn't when you get out to scry, sitting back where it was. Okay, so then yeah, anyway, so we could ask questions about fermions and so on these backgrounds and so on. But the okay, so how do we do the 2-point functions? Well, we're just looking at these integrals on the background here. So we've got so first of all, we're thinking about this as being part of a SU2 Yang-Mills field, which is basically just sigma 3 times the dion. So it's a diagonal Yang-Mills field. And then we're thinking of these as being anti-self-dual perturbations in the off diagonal. One has charge E and the other one minus E. And you just perform that integral. And there's a similar thing you can do for gravity, and we use the Pavansky action, which gives you so the gamma 1 and the gamma 2 are the 2 anti-self-dual fields, and the variation of this anti-self-dual spin connection, and this theta here is the background. So these are concrete integrals that you're led to. And you discover that the plus plus and the plus minus cases vanish as you expect, but the minus minus case gives you actually something non-trivial. And the sort of integrals you get, I'm running out of time, aren't I? Okay, you don't see what the integrals you get, but you can do them.
Maybe 5 more.
Well, okay. So you get integrals like this, but they're rational functions, and you can sort of somehow give them to Giuseppe, and he's sometimes does something which, well, it seems to work anyway. So it's sort of so you get some answers. So of course you get conservation of energy and charge, and well, what can I say? You get a formula. I don't know. So what's interesting here, perhaps, is that this is not conservation of 3 momentum. So the thing is going in and it's being bounced out, and so we're not just seeing straight through. It's we're seeing the bending of a negative density particle as it goes through and comes out. And with gravity, you similarly obtain stuff which and you can even do a double copy type story where I seem to have lost a bit of my slide. I see. Okay, something obviously went wrong with my. Oops. Okay, so you can you can even sort of see that these are almost the gravity one is almost the square of this one, but for a factor of k1 plus k2 squared, which is now missing. And I guess you have to sort of close your eyes and say that with this substitution that the E is 2m omega, which is what we had in the solutions, that this factorial squares to give that one, which is obviously it doesn't quite do exactly. So, but there is a sort of a double copy story there, even if you have to half close your eyes to see it. So we've already talked quite a lot about the Newman-Janis trick. So this was basically saying the self to your sector is pretty trivial. You just shift your x by minus IA, and you don't need to do the anti-self dual pass in the opposite direction. It is just there's nothing cunning to do in the self dual sector. So the spin version is obtained just by analytic continuation, this imaginary translation. And the way that you see this in the calculation is basically that you can sort of start off with momentum eigenstates that are sort of doing the right thing on the real slice that's associated to this shifted real slice. But then when you push it back to the one on which we did the calculation with deform the contour to one which you do the actual integration, you just get a factor of e to the minus k dot a for each of the particles. And so all that happens is you get this extra exponential factor in the final answer. And the nice thing is that that then agrees nicely with the famous amplitude that Akani Hamid and Wang wrote down. Yeah, anyway, so this really agrees with their guess. So it gives you a nice way of seeing how it is that their guess could be coming about. Is basically because you're only really looking at the self-dual part of the spin. You don't need to cope with what would happen with the anti-self-dual part. Okay, so we have explicit formulae. They describe the helicity flip of an anti-self-dual particle by an anti-self-dual background, but it has non-trivial scattering. It's going through, it's coming out with a different momentum. And the reason why we could do that is because of the integrability of the self-dual sector, but we sort of hid that in some sort of nice identities, the existence of a Killing-Spinners and structures. But in principle, this is resumming infinite many diagrams. So what could this mean for real scattering on real backgrounds? So to get a real background, you'd have to somehow incorporate the anti-self-dual part of the black hole as well. And the two anti-self-dual particles that we are talking about in our two-point function shouldn't interact with the anti-self-dual sector by the same kind of logic that I was using before. It's a hand wave. So it should, in some sense, agree with the Lorentzian answer with a complex conjugate anti-self-dual sector. But the problem with this is that kind of argument doesn't explain to you how to get rid of the nut charge. And of course, the fact that we've got this growth and all that sort of thing suggests that our calculation is probably telling you about how to do a nut or Kerr-nut scattering, not really sort of without the nut parameter. And so this may be a reason to sort of try to sort of think about how to do this in split signature, because then you can ignore the topology. It's just that we haven't figured out how to use split signature. So the split signature might give you a way of sort of ignoring the topology, and then you could somehow suggest that means that, morally speaking, you've found some way of setting the nut charge equal to 0, but we don't know how to do that. Just for future directions in the last minus however many minutes, we've got these charge Killing-Spinners, and they arose from twistor space, but what can they do for the full Kerr? Some of these structures exist in the full Kerr. They said that the thing that obviously won't exist is this lift from the self-dual diamond to the solution. But is there something? I don't know. It's so well studied, it'd be very difficult to imagine you could find anything new there. this was really part of a project in which we were trying to do the multi-particle amplitudes. And there you really do need the twistor theory. I couldn't sort of derive all this without that. So this will be following what I summarized at the beginning. But there's a lot of details to fill in with the integrals and stuff. I just think it's a cute idea that you could actually be trying to scatter linear anti-self-dual tab nuts in the full self-dual background. I mean, that could be another route in. I mean, route into studying black hole scattering. I mean, but there is just this more general question of how do you take this sort of approach, which is a little bit out there compared to the mainstream community, and actually close in rigorously on conventional conservative calculations. And I think, well, I hope at some stage we'll be able to answer that more clearly. So I should stop there though. So thanks very much.
Hi, this is a good talk. I'm not super familiar with what's, so I was curious about the anti-self-dual particle scattering of the self-dual background. In the
Yeah.
sense that, so you made the statement that the plus that scattering amplitude is zero. That's like a statement about integrability. And
So the all plus is a statement about consistency. So that is to say you can't create a minus particle. If you just started up with self-dual particles, you never create an anti-self-dual particle. So that's just telling you that the equations themselves are consistent. But the integrability is where the one minus, you see, in order to detect a plus particle, you've got to take an in product with a minus particle. So the one minus would be then telling you if you've somehow changed your plus particle as you go through the space time.
yeah, so I guess it's a statement about the conserved quantity that that amplitude disappears. But it seems like with the minus there's a change in the momentum. It goes
Yes.
like the momentum coming is different from the momentum coming out.
Yes.
And my confusion is that normally when there's integrability, then one of the, at least in the current case, like energy is one of the conserved quantities, but it seems like, or momentum, but it seems like that's
Well, you do get scattering. I mean, particles go in with one. I mean, there's an angle, I guess.
yeah, there I guess I guess so it's not okay, so it's not that it's physically
So the energy was conserved.
the energy
absolutely.
was conserved, but physically that momentum is
Yeah.
not conserved, but there still
Yeah.
is some number of conserved quantities.
Yeah. So the angular momentum obviously has to be conserved.
Yeah.
Yeah.
Okay.
Well, any more questions? Otherwise, we can go for lunch.